So today we'll start out with a little bit of review as usual, but we'll review the general high-level concepts of quantity takeoff as we've talked before, and then we're going to dive into quantity development for pipe most specifically, and we'll talk a little more quickly, a little more high level about Softcraft and their basis. So they kind of tie back into everything in reality. So review. The process of converting drawings and specs and lists into quantities is also called quantity takeoff, material takeoff, which is the quantity development acronyms. And the quantities represent material, but they also represent installation activities, and they very well may represent several activities at one time, as we talked about the sheetrock installation, the tape and float, the texture, and the paint. It can the one quantity can represent all four of those activities. Key quantities are not just the accumulation of the quantities, but they're specific quantities, and they're important to know and to be and defined and follow because they establish the basis of ratios and metrics by which you measure and analyze your estimates at a high level. And it's important to know your company's guidelines because many companies vary in what their definition is. Today, again, we're going to talk about piping, but that means piping, not tubing. Tubing is not included in the key quantity of piping. Allowances. Now, we know that whenever we calculate our quantities off the drawings or pull it out of a model, those quantities are neat. They represent the actual intended final product, but we know that reality always changes that slightly. We've talked about it, forms bow, and we pull cable beyond the tie point and make sure there's slack in there, and we cut off and drop some on the ground to when we get the exact length we need. So there are practices of assigning allowances to the quantities to account for various things. Maybe it's just a design change by engineering even on a piece of equipment. So design allowance is something we need to align with our engineering counterparts because they know what the potential change is for a particular piece of equipment or concept. The MTO allowance, on the other hand, really reflects the phase or the FEL phase that you're working in, because the earlier you are in the process, the less everything's defined, and engineering's guessing, and everybody is guessing more and more as you move backwards in the design process. But then, in addition to that, you have the impact of who is actually performing the takeoff, the time that they're allowed to quantify those items, and the methods and tools they use to generate it. So as the experience drops, as time is squeezed, and as the tool becomes more conceptual, that too will impact your MTO allowance, which is actually you're trying to define what you think the gaps may be, how accurate you think they took off, what's actually there. So the FEL phase will establish a level of development, and then these other aspects are trying to quantify how well that level of development was addressed. Waste or construction practice, on the other hand, like I was saying, if you have to overpull cable so that you have slack in the line and you have extra slack to make sure you can terminate well, when you cut that and drop it on the ground, that's just wasted material, and it varies, 5 to 15 feet or more on each end of the cable. Well, that's a practice. It's not that we have one person that does it and everybody else pulls it just right and maximizes the cable. It's a regular practice. So you have that in a similar occurrence in pipe, and you have that practice in cable pulling in particular. Overbuy, it's a repercussion of two variables. One is people tend to buy more than they need at times, and now you have surplus sitting in the warehouse or the connexes. But then also you need 150 feet, but it only comes in 250-foot rolls and something of that nature. So you end up buying more than you really need. Some of that can be reused in the future. Some of it just disappears in time. But it's also important to know this is not contingency. So these are specific focused allowances placed on particular items that are deep, deep in the DFC development. And so even though they're contingency like in their essence, they're not contingency, but you also don't want to you don't want to put contingency over the top of everything to account for these items because they're already accounted for. The reason they're not considered contingency is because contingencies you're applying to the whole project at a very high level. So it's very generic. You're trying to define contingency topics, but you're not at this level of detail whenever you're applying it and calculating. While these are very specific, they have specific purposes and they're being applied at the granular activity or line item level. So they do vary. So again, what we are going to talk about today is piping, and the key quantity for piping is lineal feet. So it's important that as you set it up, that the pipe gets that lineal foot unit of measure, and then everything else that you add into the piping MTO does not. So you could put LF period, you could put FT, you could put each, you could put lump sum, you could put lot. There's many other things that you could use that would signify what the unit of measure is that the quantity is based in, but it needs to be something other than lineal feet so it will not roll up. So what all am I talking about that's included with the pipe? You have the pipe itself, whether it's straight run or spool. And then you have what we call the fitting mix, which is flanges and fittings. Now the flanges are flanges. They kind of stand alone, but the fittings could be elbows, T's, Y's, crosses. They could be 45-degree elbows. They could be 90-degree elbows. They could be reducers. And if anybody wonders about increasers, an increaser just doesn't exist because you just turn the reducer in the reverse direction. And but rarely does anybody go from small to large. It's normally reduced, therefore they're called reducers. Valves are counted separately, but they're part of the piping discipline. Specialty items, so hoses, strainers, inlets, specialty quick disconnects, inline items such as inline mixers, expansion joints. There's a lot of variable items that change from project to project and process to process that may be inside the pipe run itself, but they're not pipes. So they're basically just called piping specialty items. Not to be confused with inline instruments, though. So you could have orifice plates, you could have control valves and things of that nature, and they're not specialty items. They're actually instrumentation. Wouldn't
it depend on the contract what they call them? Because not all contracts are written the same when it comes to control valves and XVs. If it's a specialty pipe or if it's an instrument.
Well, normally instruments are fairly consistent in their definition, and then anything else that's in the line would become a specialty item. So I've never seen in any job that I've ever been on, I've never seen control valves or considered specialty items. Now, I will have to give a little bit of a caveat. I do believe that I have seen orifice plates called out as specialty items before. But
You should come to
typically,
work with me.
why? What's that?
It's the thing we're doing now. Is there's a big argument about what's considered instrumentation and what isn't when it's on the pipe, because they want to change the philosophy behind it. But
Oh,
just need to hear.
somebody trying to change the billing or the earn value associated with it.
Yeah, what they call it, because it's different values.
I see. Yeah, now you got people trying to play games,
Yeah.
which happens all the time. So,
Where would you capture vents and drains? Would you just count that in your valves?
vents and drains are in the pipe, but they're really just fittings. But the reason well, I was going to say they're different, but how we consider them different or not depends on when they're installed. What I'm driving at is drains and vents and drains that are in the drawings and are shop installed just would fall in our fittings definition. At least at least the T or the nipple would, but the plug that fits on the end, or even weatherlets and socklets, we typically consider fittings as also. So, but if we then have to install them in the field because the isometric wasn't complete enough or put them in the wrong place, and we realize that we actually have a high point that has no vent on it, then we have to cut them in the field, cut and weld them in the field. And from that standpoint, we don't put them in fittings or specialty items. We consider it part of our testing.
The commissioning valves.
Or the testing of the pipe, where when we have to pressure test it. So after
Steam blow it.
Well, after that, so
Okay.
we'll end up pressuring it up using water. Well, it depends on what the pipe's for. It could be
Yeah.
nitrogen or argon if it's a air valve,
Air. Yeah.
airline. But if it's a line carrying liquid, we'll use clean water, pressurize it to roughly 110, 120% of design pressure.
Pipe spec or design pressure. Yeah.
Exactly. And then when we're done, we'll drain all that out, and depending upon whether or not we need to reuse it or have to get rid of it, we'll do something with it. But then we'll blow it after that.
Do you see issue with considering vents and drains as a pipe, because pipe spec will dictate what the vent size and drain size is and the service?
No, it's common practice to consider that part of our
Okay.
pipe.
Okay.
But it's
I'm
just
just
the main difference is when we install it. So, and it's I'll tell you what, we'll talk about that further here in a minute, because I'm going to
okay.
separate the two.
Yep, I got you.
So specialty items, again, I listed off a few plugs or another one, and then miscellaneous supports and hangers. When we categorize these, when we pick these up, it's usually an allowance. We don't go into detail, but we're talking about all thread rods and unistrut type bars, where it's all in the field, and you're determining where to place that hanger or support as you go. So it's in a non-engineered location. If it's an engineered support of some kind, a T-post, a kicker off of a column, those are all engineered, and they're going to be normally fabricated by a steel fabrication shop, and they'll fall in steel. They won't fall in pipe. So the same type of miscellaneous supports and hangers that you would see holding up cable tray and conduit is similar to what we would include here. A couple other things that just came to mind that I didn't mention a second ago on the specialty items are special hangers. And what I mean there is I just mentioned the all thread and the unistrut. And for those of you that aren't familiar with what those two items are, all thread is literally a bar that you can buy in 10-foot pieces, and the entire bar is threaded from one end to the other. It's, you know, where you might look at a little screw and only the, you know, 2/3 of it's threaded, and then the 1/3 at the end where the head's at isn't. Cut that end off, and you've now got a little bitty bar that's all thread. Well, picture that 10 feet long and 1/2 inch to 3/4 of an inch in diameter. And then the unistrut is like a tube, but it has holes all through it. It looks like Swiss cheese. And so it's designed so that you can install the all thread wherever you can find a place to install it above, bolt it in place, and you should be able to slide through all the holes in this tube, slide it up. And so it's very forgiving in where you place that all thread, and then you tighten the bolts up, and you lock that tube in between 2 or 3 nuts on that all thread with some washers, and lock it in place, and then support the pipe at that point in time. On the other hand, the hangers that I'm talking about, they're pre-designed and manufactured can hangers, and they have springs in them, and they operate in 2 ways. One hangs, and then the pipe hangs off the bottom of it, and it's literally the pipe is on a spring at that point in time. So if it cools down and heats up quite a bit, has a lot of movement, that can hanger will accommodate that movement. Or it can be the other way, where it's sitting on the ground and the pipe sits on top of it, and then so it's still on a spring that way, but it's being supported from the bottom instead of hanging from the top. So those are they're strategically placed depending upon where the engineers determine there's going to be a lot of pipe movement. So all of these items belong in the piping category, but only the pipe is counted in the key quantity. And I'll go ahead and say it now, and I'll repeat it in a minute, but the pipe length that you're including in this key quantity is the through fitting length. It's not the actual length of the pipe itself. And I'll explain more what I mean by that. Does anybody have any questions before we leave this slide? Okay.
I just wanted to ask a question. What is spool again?
What we're looking at, a spool right there in that picture. Is that?
Okay, it's like a section of the pipe.
Yes. Can y'all still see that? Because my red line,
Yep.
my window around it is not visible. So, okay.
Spool can be also a double flange piece that you would roll out.
Say that again.
The spool
Mhm.
piece, it could be double flanged, so you can roll it out with a pipe, especially like in a decoke unit.
You mean just have a flange on each end?
Yeah, so you can unbolt it, roll it out of the way when you decoke a unit to keep it from plugging off.
Oh, sure. Sure. I mean, you can have a spool can have no flanges on it, or a spool can have flanges on every connection. It just depends on what the design basis is.
Yeah, what you need it for. That's right.
Yeah, what you need it for. Usually, if it's pipe to pipe, it's welded, but if it's pipe to a piece of equipment, it's flanged. However, you just brought up a really good point, and that is if you have a piece that needs to be removed periodically, and the engineers know that as they're designing it, then they'll put a flange on each end of that particular spool, whatever the design length is, so that it can be removed, and access can be granted, just as you were mentioning. So the main topic. Well, that's not really the best way to say it. There's two keys approaches to fabricating pipe to keep in mind, and one is the concept of shop fabricated pipe and field fabricated pipe. And even though we say field fabricated, the field fabricated pipe usually is still partly fabricated in a field shop versus a third party's shop somewhere. And the importance of these two is the similar concept to modularization, if you are familiar with that. Shops are in a controlled environment inside. They can be enclosed whenever it's raining. You can air condition it when it's really hot. You can open up and let the wind blow through when the weather's nice. It has bridge cranes in it. It has welding machines and grinders and everything strategically placed. You've got stands everywhere that you can use. It's on a concrete smooth floor, so you can move things around easily. And so the main concept is that you are fabricating pipe spools in a controlled environment that is set up to support efficiency in the craft. In addition to that, the craft that work there all the time. So just like office personnel go to the office every day, they go to the shop every day, unlike their field counterparts that are constantly traveling around the region and around the country to a different job site, and they're having to live out of a trailer or a hotel or a rental house or something. So consequently, because they get to stay home, they're paid a little bit less typically, and they don't require per diem because they go home every night. In addition to that, the shop is run more efficiently than the field is, so the overhead costs are lower. So consequently, you end up having a product that the quality is equal to or better than what the field can produce, and you reach that point in less time, and the cost per time is lower. So it's quite a bit cheaper once you compound all of those savings. Where you lose some of it is that you have to transport everything to the shop, fabricate it all, and then transport it from the shop to the site versus just transporting everything directly to the site. So there's a little bit of cost savings reduction in that activity, but freight's usually not over the top. In addition to all that, the shop, once they're finished fabricating it, they will perform x-rays there. They'll perform any other inspection requirement. Usually there's usually a minimum of 2 requirements: visual and x-ray, visual and dot penetrant and x-ray, visual and radiograph, something. There has to be typically two different types of tests performed. Then they'll hydro test it, then they'll blow it and clean it there. And then if it has to be post-weld heat treated, they'll take it there, and then they'll send it off to a shop to be painted. So it's even shop painted as well. So when it arrives on site, it's finished coated and ready to go. So usually at the end of a job that's highly shop fabricated, most of your painting activity is touch up. It's not actually putting on full systems. I think that covers that one. So the flip side of that is field fabrication. So I believe, my experience is that in years past, shop fabrication wasn't quite as proliferate as it is now. Now we try to shop fab everything we can to the maximum extent possible. I know when I first started years ago, we typically tried to shop fab everything that we could over 4 inches, then it became 2 inches, and now we'll even try to shop fab our small bore, which is anything below 2 inches. The problem with that is that when you start getting to the small bore items, they're not really engineered. And so it's very difficult to shop fab that too much because there's no drawings. So they have to be very general in what they fabricate. On the other hand, the field fabrication, some of it you're actually, like you see this picture here, these guys are welding in the dirt at the final installation point. But they're going to try to keep that to a minimum. So there'll be an on-site fab shop that they'll assemble the majority of the spools. And so you're saving the productivity from this situation, but you still aren't quite to where you would be if you were in a regular third-party shop, because the shop's makeshift. The craft still are having to travel there from wherever they live to the sites, so they're still incurring per diem. The shop is not as complete, complicated, and thorough as a third-party shop that everybody uses every day. So again, it's a temporary facility that they're using, but they'll go through the same procedures. Well, they'll have to measure, cut, bevel, tack, weld, then visual inspection, and then some type of x-ray or radiograph, then hydro test, and blow it after they're done, and then paint it. Post weld heat treatment then is only done on welds that require it. What welds require post weld heat treatment? Welds, carbon steel that's over 3/4 of an inch, or alloys. A lot of alloys require it. And for those of you that aren't familiar with what post weld heat treatment is you literally are wrapping the pipe with heating coils that will raise the temperature of the pipe up to the point to where the pipe's glowing. I don't know the exact temperatures, but it's extremely hot. And then they will slowly cool the pipe back down in a controlled manner. The reason is that when you have very thick walled pipe, as you weld, you're turning the metal into molten liquid, and then it cools. And the liquid is very, very hot while the cool is not. And so as you're pushing that bead around the weld, you're heating up part of the pipe while the other part's cool, and it all starts. It's not even, number one, and number two, if it's too thick and it cools too fast, you start having fractures in the steel. So the way to avoid or thwart that development of fractures is to heat it back up to a required temperature and then slowly cool it down. Because, and a lot of that has to do with the thickness. That's why, if it's under 3/4 of an inch and it's carbon steel, you rarely do you require it. I don't know of any circumstances that we've ever done it in that. But again, if it's an alloy, stainless, I believe, requires it. I know it requires argon backing as well. You'll have to post weld heat treat it, and there's a special group of guys that come out and they wrap it and they perform that test, and it's somewhere neighborhood of $500 a test for like a 12-inch, 14-inch type pipe, and it gets a little less expensive for smaller and more expensive for larger. But they'll run 2 or 3 post weld heat treatments at a time to keep the cost down some. So, but you're still looking at $350, $500 per heat treatment. I don't think there's anything different. So the fabrication of the spools is pretty much the same as what we were talking about before. Spool piece is going to be defined by the drawings, whether it's welded on each end once you take it to the field, or it's bolted up, flanged. The configuration of the spool depends upon the isometric that you're building it to. Again, the small bore that I mentioned earlier usually don't have isometrics. They're usually what they can consider field run. So where field fabrication is being primarily fabricated in a temporary facility in the field and then finished out in its final installation point. The field run pipe, the 3/4 inch, the 1 inch, maybe even the 1.5 or 1.25 inch pipe, it's literally being fabricated in place, almost 100%. And if they can pre-cut a few things, maybe weld a few fittings in the shop and then take it out, they'll do as much as they can. But since there's no drawings, they normally have to snake that pipe through the process unit as best they can. And that's why it ends up being field run instead of fabricated in a shop. So going back to what we were talking about earlier when Stephen brought up vents and drains, is if you can picture a spool like we had right here, going the wrong direction here. You can picture this size. This one here looks like it's about a 16-inch diameter line. It could be 4-inch diameter. It doesn't matter, but it's fabricated in the shop. It gets sent out to the field, and because of the actual final angle, you find out that the high point is right here. And as you start to pressure everything up, if you know the high point's right there, you can't just leave it alone. You have to put a vent there, because what will happen is as you press everything up, that you'll have an air bubble form right there. And that air bubble becomes highly, highly pressured, more so than the water, because air compresses more and it becomes dangerous. On top of that, you won't ever reach your full pressure because you're continually compressing that air. It will continue to compress while the water hydraulically will only compress so much, and your pressure just starts building much quicker. In the meantime, if your high point's here and your low point's down here and there's nothing there, you need to put a drain on that end. So you close the drain, fill it up with water, open your vent until water comes out, close the vent, and now you're full of water. And then you pressure it up to the design pressure plus 20%, whatever the spec calls for, and you hold it for a while. So 10, 15, 30 minutes, an hour, whatever it's called for. And when you're done, you relieve the pressure and then you open the drain, everything drains out. So if you don't have a drain at the lowest point, you won't be able to get all the water out. Even when you try to blow it, there'll always be a little bit that stays in there. If you don't have a vent at the highest point, you'll never get all the air out and get your pressure test up to the maximum pressure that you need to. So that's the reason that they're required. The difference between the two is noticeable when it comes to cost, because if they cut them in properly in the shop, then it's just the cost of another weld and a small piece of material. Usually it'll be like a sockolet with a nipple on top of it and a small flange, and you're done. On the other hand, if it gets shipped, they find out in the field that it's not there, they got to do all that in the field. So now you've got the higher wage rates, with the per diems, you've got the less efficiency. And so it will literally change your pressure testing costs from 5 or 6% to about 15% of all your pipe. So it becomes a notable adder if you can't get them fabricated in the shop properly. But the shop is only going to fabricate whatever is on the drawings. And that goes back to what engineering designs, and sometimes engineering can see it in the models and sometimes they can't. So you just have to have faith. You have to figure out how much faith you have in the quantities that you've received and the designs that you have as you start trying to plan that out.
Professor Whitman, Where
Yes.
would you account for storage? So if you got a vendor that's making pipe and they store it on site, they're gonna charge a storage fee. Would you count that miscellaneous or would you, or just indirect fuel cost?
Normally, we'll have them ship it to site. We store it in the laydown yard. It's part of our indirect field costs. It's part of the cost of setting up the field, and then our crafts that are receiving, checking, setting, then picking, staging, and then taking it out to the craft to install. On the other hand, if we know ahead of time that there's going to have, there's a, let's say, we have a known undersized laydown yard, and we have to start talking with vendors to hold things back, then we will basically get a quote from them for what that cost is.
Mhm.
It'll become part of our material costs. We'll just roll it in with the same. I mean, we might make an effort to break it out and put it in with maybe our freight costs or something like that. But in a lot of cases, I think it'll end up falling in your piping because they'll just quote it with the fabrication cost and it all gets rolled together. It really will come back to how close is everyone paying attention to the details. I think if you wanted to keep all costs really tight where they belong, it would be best to break it out and drop it into your indirect costs and say this is storage costs from them for this. Otherwise, it would have been a laydown cost. But honestly, we estimate at about the 5-foot level, and everybody tracks costs in the field at about the 100-foot level. And that's because it takes labor to track the costs, and everybody's trying to be as low cost as possible. So therefore you can't afford to do it. So we will estimate individual fittings. We'll estimate welds separate from handling, separate from installing the specialty items, separate from installing the valves, and separate from installing the miscellaneous hangers and supports. And in the field, they track pipe.
Okay.
So the way we know whether or not it's right or how close we were is we roll all of our stuff up to the key quantity and then compare it to what the field costs were. And if we're high or low, we have to investigate, well, hey, how did it go? What happened? And then kind of verbally walk our way into it, which we rarely have that opportunity.
I
So
don't want to jump ahead or anything, so stop me if I am, but you wouldn't measure all pipe that's in linear feet and have the cost be the same because your CS11, CS12 is going to be more or less than your CA11, 12, right? Or do you account for that later when you assign a value?
no, when we're estimating, we estimate all the material types separately.
Okay.
But whenever they are tracking it in the field, they might go as far as to separate it between materials, but normally we just get pipe.
No,
Everything
we
rolled together.
separate the project I'm on. We separate, and they're very anal about it.
Yeah, it's and the reason we don't, like I was saying, it goes back to you have to have someone, you have to have enough field staff to be able to track the labor separately and also track all the materials separately. Materials are a little easier. You can have someone deep dive in and separate all the POs, right?
Yeah.
And you could get there, but you never get the labor there because you're going to fight like these fellows that we're looking at right here welding this piece of pipe in the field. You'd have to get them to account for a different, or maybe not them, maybe they're foreman, but either they or their foreman are going to have to account for their time differently every time they weld a different spool, a different piece of material type or something, and they're not going to do it. You have to really incentivize them to get that detailed in their timesheets, and so it ends up being lost because they're trying to blow and go, And if we start going, hey, you got to track all this stuff, they're like, you're slowing me down. You're on me to weld the pipe, but yet you want me to take care of this paperwork, and it's wasting my time. So it's just kind of outside of their wheelhouse in a way. And by the time you get to somebody that actually would care any, they're so far away from it, it's not going to happen. And so we can't afford to do it because it's just going to erode our margin, and the clients normally don't want to pay for the extra. So years ago, I think it was more common, but as things keep getting tighter and tighter and tighter, we keep finding higher, more efficient ways to count things, and things are getting slowly dropped out as that happens. And so,
All right, well, I'm gonna need you to email Chevron Phillips about that.
I don't. There are certain things I may not repeat outside of this class.
Okay.
You know what I mean?
Yeah, I gotcha.
But the truth is that most everybody's unit rates that they're using today, and you pick any company, and they may give you a long spiel about how great everything is and all that they do. And you pick anybody, I don't care. I won't call them a liar to the face, because I may need to call them for employment one day, but I'm going to tell you, they're going to give you a nice clean story. But at the end of the day, most everybody's unit rates that they're using today are still based on those rates that were built in the 60s and 70s. What they've done is they've normalized them. They've done some studies and said, well, we had all these productivity studies back in the early 70s and the 60s, and maybe in a little bit into the early 80s, but mostly the 70s and 60s. And we know what it takes to weld this and to weld that and to lift this. And even though we have better equipment now, you still need a crane that can lift so much, and you still have to set up the rigging. And even though we have automatic welders, the time you save in automatic welder welding versus a craftsman welding, you lose in the automatic welding setup. So it ends up being the same, pretty much. But the safety requirements today, now that OSHA has stepped up and said, you can't, you must, now that has really slowed things down, right? Where guys used to walk the steel, now they have to scoot. Where you used to be, you're just free walking up there, and hopefully you have really good balance. Now you have to be tied off 100%. So you got 2 lanyards. You have to be tied off, you're more than 4 feet off the ground. There has to be a lifeline. You have to have fire watch and hole watch, and it has to be snip tested before you can walk in and start working inside confined space, and so on and so on. The stretches in the morning, the JSAs in the morning, all of these things, it all costs money through efficiency. So there's been a lot of efficiency loss, but we're a lot safer, because now it's a big deal when someone cuts their finger. It used to be a big deal when someone was decapitated, right? So we're at a much safer level today than we were back then, but it's come at the cost of productivity, and which means things cost more. But the base rates are still there. It's just everybody stepped back and they've kind of said, well, we know based upon all of that old stuff that it takes this long to handle and do things, because we don't do things that much differently today. It's just our equipment's a little better, but it's still similar. But we recognize a little bit of efficiency gain with the new equipment, but we recognize the productivity loss with the practices. And so now everybody's readjusted their rates to equal what they think it is today, but it's still sitting on top of those old rates. And really, it's not that bad. I'm just trying to say that's where it's come from. But if everybody thinks that sounds really bad, remember that the computers we're using today are still sitting on top of DOS. DOS is still underneath all that. It's just that the GUI interface keeps it hidden. DOS was really big in the 70s, and created in the 70s, and it was what we used in the 80s, right? And
So
now
it's the biggest money maker for Microsoft till today, believe it or not, the licenses for it.
Oh yeah, it's I mean, it's still, the old DOS is still alive and well. If you could get behind the GUI, you knew all the DOS commands, you could move
Right.
around in that way. So it's the same concept, we're doing more with the old data.
Yeah.
So didn't mean to go off track too much with that, but it kind of relates indirectly to what we were talking about tracking, and that is back when things were more manual, everybody tracked things more closely. Now that things are becoming more automated, we're trying to move faster and faster and faster. Data is moving faster and everybody can track it. Plus, no one wants to pay for the manual ability to track things in the field, such as what the crafts are charging to at a real finite level. So we use that old data that's been massaged to current, and then they track the cost at a level that the project will be willing to pay for. And then we roll our costs up and compare the two. And so the assumption is if they're close, then you're good. But if they're not that close, then you have to do some analysis and some investigative guesswork as to, well, where is it that we think we're off? And that usually will take a little bit of manual effort to get in there. Did that answer your question plus some?
Awesome. Think we got it.
All right. So moving on. Now MTOs. All right. So we talked about what's in the pipe, and we've talked about the two approaches to fabricating the pipe before you install it. Where does the MTO come from? Which is the primary focus of this particular module. Well, it can come from 4 different locations. One, it's engineering provided. So the engineers build a 3D model, much like what you see here. This is a snapshot of a smart plant. And they will, when they're finished, they will drop the quantities out. They'll download it, and they'll send it to you in a format that your company is predetermined as the procedure. And then the estimating system knows how to read that, and the estimators know how to process it. Another option is to model it on a more conceptual basis. So the Smart Plant 3D, they're actually building the plant in that. And so it's progressing as you work through the FEL stages. If you're early and you don't have the time to do that, there are some other options that are more conceptual, but actually have the ability to feed into Smart Plant. One is OptiPlant, and OptiPlant and Smart Plant look fairly similar, but OptiPlant is more basic. But you can, we actually use OptiPlant in our estimating department. If engineering hasn't had time to go there, and we can, as long as we can get a plot plan, it can identify where everything's at, and then our estimators can start running each line. It just says go from here to there and take this path, and it will start auto routing the lines, very much the same as Smart Plant. The difference is that Smart Plant has a little more data behind it. Smart Plant will run interferences. Smart Plant will do hazardous analysis on it. There's just more to what Smart Plant's doing. Meanwhile, OptiPlant is working at a higher level, but it generates a quantity. It's more conceptual, but it's still there. And actually, when we do this, it generates a tangible quantity for us to price and labor, but then we can hand the files over to engineering. Engineering can load that in the Smart Plant, and they're already that much farther down the road, but then Smart Plant knows how to add more spec to it, and the engineers can modify it as they need, but they don't, even though they may have to modify it, they don't have to start from scratch. So we're still saving them some amount of time and effort. Taking a step farther back in moving even more into conceptual view is ACE. ACE is Aspen Tech's capital cost estimator. It's actually an estimating tool, and it's a very complicated estimating tool. It's not like most of your other programs. I like Timberline. I'm a fan of Timberline, but Timberline, like all the others, comes as an empty box, and you have to load in your wage rates, and you have to load in your productivities, and you have to load in your material costs, and normally you have to load in all your quantities as well, unless you spend months, days, years, hundreds or thousands of hours building. Actually, it's not hundreds, it's going to be thousands or 10,000s of hours building models in it. It has the capability of building models, but not to the degree that you're looking at in this picture here. They're mathematical models. But ACE already comes ready to go. ACE, the estimating system, sits on top of a myriad of engineering algorithms. So when you go into ACE and you tell it, I want a compressor that is so many horsepower, and here's the specific gravities of the gases that it's moving, and this is the style that we want, it will generate a compressor for you, a size, a weight, and a price. If you tell it that you want a pressure vessel and it's going to hold so much volume at so much pressure and so much temperature, it will design the pressure vessel for you. It has that capability. In addition, it has built-in standard P&IDs in it. And so whenever you pick a piece of equipment, it automatically carries with it a certain number of instruments and a certain number of wire and size of wire. And it will change the size of wire based upon the horsepower or whatever it is, the heating capacity that you're picking with that equipment. And you can go in and tell it you want volume around each piece of equipment. So the bigger the volume, the more cable, the more pipe, the more tray, and everything will give you. The weakness is that it has some gaps. It doesn't do pipe rack corridors, and it doesn't do the general plant site. It won't do your parking and area paving and things of that nature, because it doesn't have anything to tell it what it is. But it will do all of your process work for you, and you merely need to go in and say, well, we know that we've got our core pipe racks running in these directions, and it will build the pipe racks and put the pipe in it for you as long as you tell it what it is. And then you go in and then you have to more manually approach the area paving those areas. But when you're done, you literally can build a plant in ACE with a P&ID, a plot plan, and an equipment list. In fact, you only need a P&ID. As long as you have the equipment list and you have the plot plan, you can build the plant, because it will do. You can make some assumptions and it will do the rest. So you can see where as you get more and more conceptual, things are a little looser, but there are tools out there that will allow you to do that versus having to sit down and manually calculate all this out, which is what had to be done 30, 40, 50 years ago. I've still got a book with formulas in it. So if someone said, well, here's your equipment list, I could go and say, well, if I know the diameter, if I know the size, or if I know the volume of the tank, and I know the diameter and the pressure and specific gravity, then I could calculate the wall thickness, and then I could take that wall thickness and multiply times the area of the tank, add some allowances for stiffeners and things of that nature, and I could calculate the weight of the tank that way, very manual, and then apply a cost per ton or cost per pound. And that's how we built our tanks at the time. and before the ACE came along. And then in the mid 90s, a very basic form of ACE showed up called Icarus. And then Icarus improved. And then AspenTech bought it and it became K-Base, and AspenTech continued to improve it and it became ACE. So it's, you know, it's sitting on a lot of knowledge and over years of development. Another conceptual approach to quantifying is you don't have any computer systems to use. So you can step back, look at your elevations, look at your plot plan, look at your P&ID or line lists, and then you manually conceptualize all your runs for each line. And if you can look at your plot plan and know where it's going from here to there, and you have elevations that show you the height increases as it's moving up and down, then you can calculate the length. And that's not very common anymore because you have the OptiPlant tools and the ACE tools. But if you don't have those two tools, the next real option you have is manually doing it, which is the way we did it back in the early 90s. Someone have a question? Okay. So it's cumbersome and it takes a lot of man hours, but it can be done. The manual conceptual approach. And if you're given, say, partial quantities and you need to finish those quantities out for whatever reason, you can always use the manual approach to add the few lines that are missing. So I wouldn't be afraid of going that way, but literally you just have to think three-dimensionally. If you look at that plot plan, you know it's going from the northeast corner of your plot down to the southwest corner. Well, you can measure it and scale it. And then if you have any feel for how tall the points are that it's tying in, it can drop down or rise up to the rack, run along the rack and you may have to guess 35, 40 feet, and then it drops out or rises out of that rack and goes to its connection point on the next piece of equipment. And you have, if you can get the horizontal length and the vertical length combined, you have your pipe run. So it's not as hard as it seems like it might be. It's just time consuming. And then the fourth is actually taking it off the isometrics. So the conceptual approaches are something that you're going to do in your FEL 1s and 2s, maybe early FEL 3. Your engineering provision is going to be an FEL 3 unless they're moving ahead and you're kind of doing some, well, engineering might actually conceptualize some things for you and then they can provide an FEL 2, but the smart plant downloads are going to come in FEL 3. And then when you get to FEL 4, they should actually have isometrics. You need the field drawing. You're going to fabricate from the isometrics. So what does that look like? Before I dive into that, I'll go and slow down for a second. Let's not forget demolition of pipe. So you have to quantify your demolition as well. But the demolition usually requires a field survey. You need to walk the field, find out what's there before you can figure out what to remove and how to remove it. Unless you're planning on reusing the pipe or reusing the valves and everything in there, you literally can blow and go as you're removing that pipe. You can go in there and cut it into manageable pieces and yank it out and drop it in a bin. You don't even have to remove the valves. You don't have to remove flanges. You don't have to remove insulation. Just cut it and get it out as fast as you can. If there's no intention of reusing anything, as you start to go, well, we're going to reuse this, or we're going to try to salvage that, you might become a little more strategic in where and how you cut it or unbolt some things to get it apart. But if you use a saw that can cut the pipe, you can cut it up and get it out pretty quickly at a fraction of what it takes to install it. because you don't have to torque the bolts, you don't have to pressure test anything. You're just cutting and going. So as fast as you can cut it and rig it and pull it out safely, that's how fast you can go. And then if you do salvage some of the stuff, or maybe you're submitting it so that you can get money for just the steel, what it's worth, you might strip off the insulation or something like that after you've pulled it out of the rack, so people aren't having to work at height. But what I do caution is that when you're thinking those that way, the pipe needs to be clean. It can't have harmful chemicals in it. It has to be signed off as flushed and able to be opened up. Normally, the client takes care of that, not the contractor, because they have the capabilities to handle those chemicals better than most contractors. There's 4 types of pipe before we get into the actual spools. Configured pipe is the most complicated. You can see here, this is a representation of what configured pipe would look like. You've got elbows, T's, flanges, reducers, couplings, everything that's required, and we call it spaghetti pipe. This is what it will look like in your process area. So if you look back in this top picture up here, you can see that there's a lot going on in that back process area. But as you move out into the pipe rack, it starts straightening out, and you don't have a lot of elbows and fittings. You have a few, but not too many. And then as you move down into your pipe lines, here, there's almost no fittings at all. You got elbows here, and then other than that, it's just running for long distances with very little of anything other than just the pipe running. So, and then there's a transition, usually somewhere in here, the pipe will become a little bit more configured, but it's still straighter than when you're in the dead center of the process area. So you have configured pipe, interconnecting pipe, pipe rack pipe, and then pipeline pipe. So not to be confused with a pipeline, it's true pipeline. So, and the reason I make that designation is that you will get a pipeline list, which is a list of all your pipes that's in your plant. So each line is a run and has its own unique number, versus, we talk about, well, there's a cross-country pipeline that we're installing. So nearly the same word, 2 very different meanings. So
but even the lines that are numbered still have a line break. Like if you carry ethylene into the plant, it's still the line number is gonna change whenever you hit a line break, though.
Yeah, like a spec break.
Yeah.
Yeah, it'll change because your pipe will, even though the wall thing is maybe the same, your pipeline usually runs under a totally different pipe spec than your plant pipe. So that's a true statement. Thanks for pointing that out. The key point that I'm trying to bring out here is that this pipeline installs the fastest and easiest. The pipe rack pipe installs the next easiest. The interconnecting that's in this area here and in this piece here running over this interconnecting area over here is the next most complicated. And then the spool pipe that's inside all these process areas that are really configured like this are the most expensive to install, because as you gain more and more fittings, it's more difficult to handle and put in place and bolt up or weld up. And as it becomes more and more difficult to handle, it takes more time. And as time increases, your cost to install increases. That's aspect number 1. Aspect number 2 is that fittings are more expensive than pipe. So an average fitting is usually somewhere in the neighborhood of 1.5 to 3 times the pipe length. So in other words, an elbow is usually equivalent to like 2 feet of pipe. Could be equivalent to 1.5, could be equivalent to 3, depending upon the orientation of the elbow. A T may be equivalent to 1.5 to 2 feet of pipe. So, but it's more expensive to make that fitting than it is to make a 2 to 3 feet of pipe. So as your configuration increases and you have more and more of the fittings involved, your average lineal foot of pipe cost increases as well. So as you move from pipeline to configured, the labor increases, and depending upon the pipeline spec versus the pipe spec that you're dealing with, the cost per lineal foot increases per diameter. So you can't just say the pipe cost per lineal foot increases, because your pipelines usually run 36 to 48 inches diameter. So they're going to be more expensive per lineal foot than your configured pipe is going to be, because it's averaging more like 6 to 8 inches. But if you had a 6 to 8 inch pipeline, the configured pipe would be more expensive if it was also 6 to 8 inches. So you have to be careful in how you compare, because it needs to be apples to apples, 6 inch to 6 inch, 8 inch to 8 inch. But the general concepts are as you become more and more configured, it gets more expensive, both in buying the material and in installation. That's important, because as you're trying to analyze what your project's going to require, you need to step back and say, how much pipeline do we actually have? Because usually the pipeline is a separate contract, but it will come up out of the ground and run inside the plant for a short distance, and then it stops. You have the pipe spec break that we were talking about a second ago, and then it continues to run through the plant, and it's still in a pipeline configuration until you start hitting your pipe racks. And then it changes configuration a little bit. It starts having more T's and Y's and I mean more T's and elbows in it at that point, but still very minor compared to configured. So you're constantly wanting to determine how much of each do I have, because if your project has a lot more configured pipe in it, your man hour per lineal foot can be higher than if it has a lot more pipe rack or pipeline pipe in it, whatever your project is. So it's a way to try to judge and figure out what you're doing. It's important from an estimating standpoint. So as you're judging, am I getting everything in that I should? You can figure that out. It's important from a project manager standpoint, because it gives you the opportunity to look at the estimate that's been presented to you and you can judge it. It's important from a construction management standpoint, because now you're reverse engineering it. Depending upon all of what I have, I need to make sure I have enough people hired, so I have enough craft to install this pipe in time. So it's helping in that planning approach.
Would you take it off any different if it was in a module?
No, the difference would be, I mean, I would still, and when I say no, what I'm talking about is we want to quantify the pipe that's quantified. That's there, one way or the other. We just want to know what the pipe is. Now, what would be different is the labor. Exactly. Because going back to what I was saying earlier, when you're in a module fabrication yard, it's like fabricating shop pipe versus field shop. And so module fabrication is much more efficient than field because of the same reasons. So normally, I mean, it's not a hard, fast rule, but 75 to 90% of what it takes in the field to install in a module. So if you got 1,000 feet, 1,000 hours of pipe in the field, might be 900 in the pipe shop. Well, there's pipe shop's gonna be closer to the 70, and the module may be closer to 85, 90. But there's gonna be efficiency gain there. So that's where that will make a difference. But quantifying it will be exactly the same. We're not really prepared to quantify the pipe that we have by giving you a tool that can do it for you very quickly. Can't give you smart plan or anything of that nature. Don't have that capability. But the piping task is going to be focused on drawings, isometric. So I want to go through those pretty quickly. So this is an excerpt of an isometric right here. And you can literally take this off yourself if you so desired, but most of them come with a bill of material. It looks like this. So if you notice, number one, 8 feet, 8.2 feet, it's a 1-inch diameter. If we go back here, you'll notice that this pipe piece right here is one, that's one, that's one, that is one, and that is one. If you notice, this right here is not one, it's actually two, because it's an elbow, right? And so here's another elbow, number 3, and here's another elbow, number 3. But this elbow and that elbow are 3. While you know what, I said that's an elbow, that's a T. Well, I missed that piece right there. So you have a T here, which is 2. You have 2 elbows that are 3, and the pipe is 1. So if we go back to here, you'll notice that number 3, 90-degree elbow, there's 2 of them. Number 2, it's a T, it's a 1x1 T. And then number 1's the pipe. And it's extra strong carbon steel, and it's seamless. It's not welded. And so as you go down here, you can see there's a nipple, there's a specialty item. They don't tell us what it is. We have to go to a specialty item list to find out. We've got a ball valve. We have an anchor, pipe directional anchor. We have an eye rod, which is kind of like all thread. It's not all thread, but it's kind of like that. And we got a U-bolt support. So if we go back here, you can see the pipe. You can see the ball valve here. You can see the specialty item right here. Number 4, what was it again? Number 4 is the nipple. So you get that nipple right there. That's connecting this end of the pipe to that specialty item. Number 7, I believe this is that support right here in the U-bolt. If I'm not mistaken. Yeah, 7's the anchor, 8 is the eye rod, and 9 is a U-bolt. So you've got all 3 of those combined here to support that pipe. And then here is a connection point, and it's connecting to a 1-inch nominal sized item here. But there's a field weld right there. See that FW? That means field weld. So we talked earlier about shop fabrication and then field fabrication. This line is a 1-inch line. So this is likely to be field fabricated. Now, whether it's field or shop fabricated, since it's actually drawn, you could shop fabricate it. You wouldn't have to field run it because you know what the dimensions are supposed to be. Assuming that it is field fabricated, then this weld, that weld, that weld, that weld, that weld, that weld, that weld are all going to be done in the shop, because you're going to make a spool. You're going to have, this whole thing's considered a spool drawing, but it actually is going to be 2 spools. Well, let's double check that before we run too fast. It's a 1-inch ball valve. It's got a 600-pound rating, and it's socket welded. So it's all one spool, not 2. And it's plain end pipe. It's carbon steel A106 grade B plain end pipe. So that means it's going to be welded. It's not threaded. It would tell you it'd have a THRD or something of that nature here if it were to be threaded. So that means each one of these connections are welds. Since this is a socket welded valve, that means each end is welded. It's not flanged. If it were flanged, then right in here, it would have an FLG instead of an SW. SW is socket weld. FLG would be a flange.
Where would they call out if it's an open weld or closed weld?
You mean
I
like
guess you really,
seal weld?
well, open welds, but they're not touching. Closed weld, the two pieces are touching, but it doesn't matter. They wouldn't put that in the MTO.
Oh, yeah, they're not gonna, that's gonna be a spec item.
Yeah, never mind. We're good.
So what, so the point here is that when, if you were to take this off and if you are having to calculate what it's going to take or cost to fabricate this item, then you're going to need to take these welds off right here. All of those, you'll have to count those welds, and you'll have to count the handling of each one of these items. And then go through what we talked about, where you're cutting, you're beveling, you're tacking, you're welding, hydro testing, all that. You have
Put it in the
all,
actual takeoff? You put these in the actual takeoff? Material
well,
takeoff?
if you're going to shop fabricate it, because all those are shop fabrication items. If you're going to field fabricate it, then you would take them all off, but it would go into your estimate. So there's where I'm driving is that if you have material pricing that says this is what your spool piece costs, then all of these welds that would happen in the shop and all the handling of these items individually that will happen in the shop, you will not include in your takeoff because it's in your material price. It's the cost of your spool. On the other hand, if you know you're going to field fabricate all these items, then you need to take it all off because the field's going to have to handle all the pieces separately, and they're going to have to make every single weld, and they'll do that in the field shop. And then this field weld here and this field weld here will be done out in the field itself, in the locations to be installed. Does that make sense to everybody?
I didn't see the second field weld. Oh, there it is. Never mind.
Yeah, right here. Yeah. So let me repeat that because I think some of you have it. If I can just kind of use my ESP, I think some of you have it and I think some of you don't. So I want to step back and I'll repeat that again. As we talked about earlier, you have two options to fabricate your pipe: shop weld at a third party location, or field fabricate it in a field shop combined with welding at the actual site or location you're installing it. That's your two options. If you're going to fabricate it in a shop, then that shop's going to give you a quote for what this pipe spool costs. And when they do that, it's going to include all the material that you see here, except for the specialty item. And it's going to include all the labor to handle it and weld it and test it. The only thing that you will take off, the only thing that you'll include in your field material quantity is this field weld, and this specialty item that you will connect at in the field. That's it. Because this valve here is welded, not flanged. If the valve's flanged, you would keep it as an item to install in the field, because all flanged connections you make in the field and the welded connections you make in the shop unless it's a specified field weld. Does that make sense to everybody? And the guys and gals that have construction backgrounds, I know are probably picking up on this, but those of y'all that don't have construction backgrounds, is this making sense to you?
You said that the flange, if on the bill of materials, it should have like a FLG or some kind of note like that that would indicate that it's flanged
Yes.
versus welded.
Yes, right here. So you can see where this says ball valve socket weld right there.
Yes.
And if it doesn't, let me see if I can open one up real quick and show you something else.
I'm just glad we're not talking about dirt and stuff anymore.
You don't like dirt? You don't like playing in the dirt?
Nope, I like pipes and process. That's my cup of tea.
Okay, can everybody see this ISO here?
Not currently.
Oh shoot, it just said Zoom quit unexpectedly. Close that. Let me see if I can re-up the screen. There we go.
So,
Can you see that
Professor
now?
Whitman,
Yes.
just a real quick question. I know we've been going over all these piping diagrams and everything, but I believe this week's assignment is the architectural interior finishes.
Nobody cares about that stuff.
No, I understand, but I just have some questions about the assignment this week. So,
Yeah, I was gonna pop up about that. It's like the two modules are backwards, 4.3 and 4.4.
Yeah, because the steel was due today and the building MTOs are due
next Tuesday.
next Tuesday. And then what we're talking about now is going to be due the 12th. So
Right.
where initially there was about a week, now you've got a 2-week window to complete them.
So we have nothing due next week?
Yeah, next week you have the building MTOs, the interior MTOs that Steven's talking about. We talked about those last week.
Okay.
I don't think we covered them, but
No,
I
I
just have
think
some questions about the assignment. That's all.
Just
Yeah.
yeah, I don't think we covered.
I think we covered the
Yeah, I
steel
don't
last
either.
week, didn't
We
we?
covered steel last week.
Yeah.
We didn't get through the yeah, I think we ended up not getting through everything, did we? We got through a lot of it, but not everything. Because the focus last week was equipment steel and the building interiors. And I think we ran out of time. That's probably part of it. Okay, let me finish this real quick and we'll answer some questions on the building side.
Okay.
Want to get a quick look here, and that is here's a flange, and it's number 14, and number 14 down here. It's a gate valve, and see it says RF, so that's raised face flange.
Okay.
So it may not have FLG, but it will. If it has an SW, it's socket weld, and if it has an RF or something similar to it, then it's going to be bolted. So another way to kind of help you see that is if right here you can see where it has that's 5. That's a slip-on flange, right? So you got a flange going to the valve. So you know that if you got a flange going to the valve must flange up. While if we go back to the previous drawing didn't have a flange there. It just showed it going straight in, and it was a piece of pipe. So so they're all labeled. And actually the one I showed you, the example that's in the PowerPoint presentation is about equal to your most complicated isometrics to take off. A number of them, probably half of them, are a little bit more this speed here. So you might want to take those first and then do the more complicated ones second after you're comfortable with it. We took off everything, but there's an aspect and we did it because of for practice purposes. So that's the goal, to take it all off. But really, when you take it off, you're capturing all this information here is what you're doing. And you're just verifying that all the pieces you see in here, you see in here. Where it becomes a little more complicated is, and there's three aspects that are a little more complicated. One is you see all the items here, identifying the items that are field installed versus shop. So this valve is field because it's flanged. The previous valve is shop because it's welded. There are a few items such as the hanger, the support that I mentioned before when we were in the previous here. This eye rod and support and the specialty item, those items are going to be field installed because they're connected to something. They're not welded to the piece of pipe. So anything that's welded to the piece of pipe, spool, will be done in the shop. Anything that's bolted or connected will be installed in the field. That's your litmus test. The next thing is, you've got all these ones that we're looking at earlier. And we said that's the pipe. And if you notice, it's 8.2 feet. And that's the amount of pipe you need to fabricate this spool. But when you go to install the spool, you're installing this entire piece from here all the way up to here to here. Then if you notice, that's about a foot. And then let me move that. So that's not quite a foot and a half. So that's almost, that's about 2 1/4. And then that's 5 feet, a little more than an inch. So that's still about 7 1/4. That's only 2 3/8 inches. So we're about 2 1/2. That's all this here is like a fraction of an inch. So we're still around 2 1/2, and that's about a foot. So about 3 1/2 feet. So this spool's about 3 1/2 feet. And that's saying 8 1/4. Doesn't make any sense. Oh, what in the world? What did I do? Sorry. That's 2 1/4, 7 1/4, 8 1/4, 8 1/2. So we're all in all, we're somewhere around 9 feet total once you put everything in here combined. Most of it is pipe though, you notice. So we're about 9 feet total, and the pipe's only 8 foot 2 inches. Now some pieces this will be around 6.5 and you'll be 9 feet because you have a lot of fittings and the fittings are long. So, but the main point is that you want to input the quantities that you see here, which are captured here. You want to input those. And then you want to go back and take the entire length, what we call through fitting length in the end, and you want to input that because that is the length of pipe you're going to labor for your field installation. The handling of all these individual items that are not in the field is what you would labor to shop fabricate. Whenever you go, when you finish this exercise, all you're doing is quantifying. You're not inputting everything. When you go to input this into your estimate, we're going to assume that it's shop fabricated. So all you will input is the specialty items, the connections, supports, the through fitting length, and your field welds. All the other everything else will be considered in your unit cost of your pipe. And I'll be giving you that.
How
So,
would you know, you mark the items that's field and the items that's not field? That's shop?
when I took it off, I didn't put anything extra in here because I knew which ones were which. But if you are not sure, what I'd suggest is say shop, and then that description, shop, that description. You get to here,
Okay.
say field SP 645, shop, field IROD, field U-bolt, field weld count, and then field through fitting length. And that way you'll know which ones are filled and which ones are not when you go back. Because that's all you'll want to carry forward to the estimate are the field items. Because I'm going to give you costs for the fabricated pipe to use in your estimates. Is everybody reasonably comfortable with this?
Professor Richmond,
Yes.
I am totally unfamiliar with this kind of drawings. Would you recommend any online resources or books that I can go through before? So I want to picture myself, at least I'll get a picture of what I'm quantifying. So do you recommend any resources?
I was looking at that earlier today because I have another request for the exact same thing. And I went back to some of the books that I have and the ones that I thought might help. I don't have anymore. I don't remember what they are.
Hey, Professor Whitman.
Yes.
I don't know if it would help, but there's process operator books that teach how to read P&IDs and PFDs, some ISOs.
Well, that's an excellent source. Do you know the name of it?
There's thousands of them. It's pretty generic. Process operator, P&IDs. I honestly would just Google it if y'all don't know how. I actually do this for a living, so I actually know what I'm talking about now.
So just Google process. What
So
should I
P&ID
Google?
stands for process and instrumentation diagram. So you can Google
Okay.
that. PFD stands for process flow diagram. So you can Google that, and then you'll find lots of stuff to read about it. And then ISO is
Okay.
isometrics.
I
Okay.
have one other book that I have. I don't have it in front of me at the moment. I'm looking for it. I'll look through it because I think it talks about piping, but I don't know if it really talks about isometrics. And I've reached back to the department and asked them if we have any type of tutorial that we can offer up for everybody that's interested, but I haven't heard back yet. Because I mean, I could spend time going through it, but I just can't. I don't have. I worked up until this class, and then I've got to go back to work afterwards for a little while.
For
Yeah, I can totally
$59.95.
I have a better question. Do we need to focus on this that much? I mean, it's good to know it, but is that like an important focus for the class?
With taking these off, well, it's one of the tasks, and it's one of the more
No, I understand.
yeah, and it's one of the more complicated topics in quantifying. This is more difficult than quantifying lineal feet of wall in a building or concrete foundations because they're usually blocks and stuff. And the other aspect, the reason why I'm focusing on it is that the two most expensive disciplines in a typical petrochemical facility is your equipment and your pipe. So as a manager, if you are looking over one of these projects, you really want to focus on the pipe and you want to focus on the equipment. If you had to pick two of all 12, 8 to 12, that would be the two you'd really dive in on. If now, on the other hand, if it's a power plant, then you'd probably want to focus on equipment and electrical, and then piping would be third behind that. But any kind of chemical process, refinery, petroleum, any of those that have a lot of equipment, a lot of piping's a big deal. And so you've got a lot of cost at stake. And so I'm trying to help you understand what's in that cost and the different ways to look at it.
Oh, it certainly is.
Yeah, as far now, I mean, honestly, going through these exercises is partly intended to help you to learn it. I'm really not expecting you to. I was expecting everybody to be familiar with it and then to leap forward and kind of talk about how to do it. Actually, how getting everybody to the point where they're even familiar with it. That part wasn't prepared to do. So I'm at this point, I'm looking, I'm asking. In the meantime, the operator manuals that Stephen mentioned could be a very good source to dive into. And then I'll also double check the one textbook that I have. I think it's talking more about what the pipe is and less about how to read it, how to read an isometric. But
Okay.
I'm trying to address that question as we speak. I just don't know if I want to have a great answer yet.
Stephen is also a good source. He has volunteered himself. I'll go ahead and put that out there. Since he likes to brag about it so much.
No, I'm just happy I'm not lost anymore. Just
Yeah,
happy.
no, we got it. You mentioned it a time or two.
Just happy. So
Okay,
no,
so
no
cap
struggle
off-
bus.
to cap off today's discussion, when we talk about Softcraft in our jobs, we're talking about painting, we're talking about insulation, we're talking about fireproofing and scaffolding. Those are the Softcraft. Even though they're different, usually the same companies that do one will do the other. There are a few companies out there that will do paint, insulation, and scaffolding and won't do fireproofing, or they do nothing but fireproofing. But that's probably a better statement. A lot of them out there, like Knight, Safe Brand, Safeway, Brock, they will do paint, insulation, fireproofing, and scaffolding. So how this translates back to the piping that we've discussed is everything is going to need paint touch up to some degree. Your equipment, your steel, and your pipe. But your pipe more than anything, because as you're installing your pre-painted pipe, you're scratching the heck out of it, and you got to go back and touch it up. Equipment gets beat up too, but not quite as bad. Steel, it gets beat up, but not as bad as pipe because it's one of the first things to go up. But when you touch up steel, you're actually touching up with Galvalume or something similar to that. You're touching up the galvanized coating on it, not a painting system, but it's still part of your touch up. Insulation, right now is a good time to mention the insulation because your piping will utilize most of the insulation that you're installing. Your equipment might as well, but most of your insulation usually goes to your pipe, and then your equipment second, and that's pretty much all of the insulation. And if you know your diameter of the pipe, and you know the length of pipe to be insulated, and you know the thickness of your insulation, add the thickness of your insulation to the diameter of your pipe, and you have a new diameter. Take that diameter times pi, and you have your circumference. That circumference times the length of your pipe will give you your area. But if you are noticing your length of pipe is going to be feet, your diameter is going to be in inches, so you need to divide by 12, and you have your square foot area. On the other hand, does that make sense to everybody? Okay, I got one thumbs up.
Yes.
Thank you. On the other hand, if you are getting a quote from one of these insulators, They will usually calculate some of that for you already, and what they'll give you is an equivalent lineal foot. So in other words, if you have a 6-inch piece of pipe and they say it's $35 a lineal foot, it's an equivalent lineal foot. In other words, that equivalent means it's in taking into consideration the area per lineal foot. So you're still capturing your square foot, but they're just saying that, well, we've got the area for every lineal foot, so it's equivalent lineal foot. And so that $35 or $45 or $25, whatever they're quoting you, is covering the area of the pipe insulation per lineal foot. That's what that equivalent lineal foot means. The equivalent lineal foot will only apply to pipe. You don't have an ELF for equipment. Your equipment will be taken off in square foot, whether it's a exchanger, whether it's a tank, whether it's a vessel, whether it's a pump or compressor, it'll all be in square foot. So you'll have two different insulation quantities when you deal with that. Fireproofing, there's only two areas that typically get fireproof: the legs or bottom portion of your pipe racks and your open steel structures. And the other would be the skirt of a vessel. So a vessel, the bottom shell may be 6-10 feet off the ground, but the shell looks like it extends all the way to the ground. And you can actually go into a manway and look in there and see the bottom head of that vessel up 5, 6, 10 feet in the air. And so that support portion is called the skirt. And it usually is as thick or thicker than the shell that runs up, because it's got to support the whole weight. But normally that skirt will be be fireproofed if fireproofing is required. The reason why everything is being fireproofed up to a 10, 20, 30 foot level is that they're trying to keep the support structures of everything from melting before you can get firemen there to put out the fire and hopefully save everything, or at least keep it. It may ruin it, but at least it keeps it from collapsing. And if you can keep it from collapsing, then you're trying to avoid major catastrophe is the purpose.
Wouldn't your fire hazard analysis call out what would be fireproofed and not?
Yes, but it'll be marked. It should be marked on your drawings as well. But yeah, that's where it's coming from. They'll do an analysis and determine what needs to be and what doesn't need to be. But if it's going to be fireproof, that's normally where the fireproofing is located. Painting, most of it's done in the shop. So what you're doing in the field is touch up. Insulation, it's almost universally done in the field, unless it's a third generation module. Fireproofing, they'll fireproof most of it in a shop, ship it to site, you erect it, and then you finish the fireproofing in the field, because you can't complete your connections if it's already coated with fireproofing. So you have what we call blockouts that at the joints, so you can connect everything. Once you're finished erecting the steel, then later on you can come back and you can cover those blockouts. If it's cementitious, you have to form it and pour it. If it's intumescent, then you'll spray it like a really heavy paint. And then scaffolding is scaffolding. It's where it's needed. The more vertical you are, the more scaffolding you're going to need. There's two different types of scaffolding out there. There's the traditional clamp it together, and there's this new what I call drop pin method, where you literally drop the pieces into a ring and drop a pin, and that pin locks it until you pull the pin out. You can erect the drop pin method up to 3 times faster than the regular bolted old style. However, it's more expensive. And then the other concept is that the people, the scaffolding personnel that are staying on site are there anyway. They're there because they're waiting for you to call and to move the scaffolding. So you get it, it's erected faster and it's torn down faster, but their waiting time is about the same and the scaffolding costs more. So in the end, it does matter which one you use. It will have an impact on your costs. You normally should be able to save some money a little bit if you go with the drop pin, but they tend to wash each other out somewhat. Unless you keep a smaller crew on call, and then you're able to see more savings. But if you're using the faster, more expedient version, you might be able to get to 10% of your installation hours. But if you're using old conventional style and you have a very vertical project, you can get to 35% of your direct hours. So literally what I mean is that if you have 1 million man hours to install all of your materials, then you're going to put on top of that 10 to 35% for scaffolding. And that it can add up very quickly. I had a job that we were working on that was 10 million man hours out in the field. And we literally were running somewhere in the neighborhood of 4.5 million hours. And wait a minute, sorry, that was no, that's right, 4.5 million. No, 1.5 million scaffolding hours in the field. It's a 1.5 million hours just focused on scaffolding. So very expensive. Fortunately, it was really 30 million hours, but we modularized so much of the scope that we moved millions of hours to the fab yard. So scaffolding is not it's not a complicated topic, but it is an expensive topic. All right, so square foot equivalent lineal foot, square foot equivalent lineal foot for paint and insulation. Fireproofing is square foot for intumescent, and it's cubic feet or cubic yards for cementitious, and then scaffolding is a percentage of your direct field labor, unless you do a very detailed buildup. All right, so next week, today was the steel, next week is the building interiors, and the week after is going to be the piping takeoff. So at that point, we will end today's discussion